Thank you, Myron, for the introduction, and thank you very much for coming out on a Saturday morning to listen to me speak about spin, magnetism, and computers. So I would like to just first start with an outline of today's talk so that you know what I will talk about. So I'm going to first start off with a very brief introduction about how computers work, and then I will quickly talk about what is spin, and what role that plays in magnetism, and how does spin and magnetism contribute to today's technology, and then briefly talk about how spin and magnetism could contribute to future technology as well. So things that are currently the topics of active research that will hopefully make devices and computers even better in the future. So how do computers work? I mean, it seems pretty amazing, really, that we have our smart devices and things that just happen to work. It almost seems like magic, but really what they do is they are able to do something really well quickly. And so the first question we could ask is, what does a computer actually do? And as you might guess from the name or the word computer, I mean, really what it does is compute, it calculates. And so a basic computer just has a few components. So it has some input, so we could give it some problem that we want it to solve. We could enter some characters using a keyboard or using a mouse, or give it a picture or something that we want it to solve a problem of. And then that information goes into a processor, and that processor will perform some calculations that or with whatever input that we give it. And then if that calculation is complex, then it might need to take many intermediate steps. So it might need to store some intermediate stages of that calculation. So just like remembering when we do like multiplication of many digit numbers by hand, there are many intermediate steps, and we want to store what those intermediate results are, and then send those steps to the processor, and then do another calculation and store that step. And then finally, at the end, we end up with our result, and we want to get some output. So whether that output is a number of our calculation, or an image that we have finished processing, or an image that would be displayed on the computer screen, this would be the output of our calculation. When I was putting together this talk, I was thinking about what my first computer was, what was my first experience with a computer. And so you can take a second and remember what was your first computer. For me, it looked like this. So this was in the 1980s, so this is the IBM PC Junior. And it was, I spent a lot of time playing on this computer, playing games because, it's amazing to think about how far computers have come since then. I mean, this computer has a floppy drive, so like a 5 1/4 inch floppy drive, a keyboard, I think no mouse. So computers have come a really long way. I also asked my dad what was his first experience with a computer. So he worked in the US Army, and he worked with this KW-26 encryption system. This is not his picture. This was from an NSA brochure. But you can see that this was a large machine, and it used vacuum tubes, and it also used magnetic core memory. And so this is why I wanted to talk about the role that magnets play with computers, because magnets have been very important for helping computers work for a long time. So I wasn't really familiar with magnetic core memory, so I looked up how it works. And if you look at, so this is an image of magnetic core memory. And if you zoom in, you can see that what it consists of are magnetic cores surrounded by loops of wire. And so the reason we don't use magnetic core memory anymore is because you can see that this was probably very time intensive and late to make, and you couldn't make it very densely. And so as other technologies were able to store memory more densely or more quickly or using less power, they tend to supersede the existing, what was the current technology. And so we don't use this type of memory anymore, but we still do use magnetic memory. So why do magnets make such good memory? Well, it's because they can maintain information about their direction. So we have permanent magnets, and the permanent magnet has a north and a south pole. And so depending on whether the north pole is on top or the north pole is on the bottom, you can use that to store the information of whether something is a 0 a bit or whether it is a 1. With computers, we need to simplify the language that the computer uses. And so in the end, the language that the computer operates with is a series of zeros and ones in binary. And so because the magnet can take these two values and store that value, and it doesn't forget the value even, so this permanent magnet doesn't require being connected to a power source, but it still maintains its direction of zeros and ones. So that brings me to my first demonstration, which is this electromagnet. Okay, so I think the reason I wanted to talk about the electromagnet at this point is because, yes, so there are permanent magnets that can store zeros and ones, but a memory isn't very useful if you can't change it, if you can't rewrite it. So in other words, you could store some information, but if you can't change that information, it wouldn't be very useful for storing, for example, the intermediate stage of a calculation. You would just have some storage, and then you'd have to throw it away and get some new storage material. But the fact that you can rewrite the magnetic memory and change whether it's storing zeros or ones is what makes it so useful. So here I have some, I think, copper wires that are just bound together. And if I try to pick up some paper clips, so one thing that's nice to demonstrate with magnets is that they're pretty strong. So I can pick up these paper clips. I can overcome the force of gravity with this handheld magnet and pick up all of these paper clips. And if I use a material that's not as magnetic, or not magnetic, it won't pick up these paper clips. But I can make this material act like a magnet if I run some current in a loop around this. So this power supply should be set so that I can just connect it with this switch. And so when the switch is not connected, it doesn't pick up the paper clips. But if I connect the switch, then this behaves like a magnet. It's an electromagnet, and I can then pick up those paper clips. Thanks, Monica. All right. Okay. So here's the picture of the magnetic field lines around the permanent magnet. And as I said before, it can store 0. And then similarly, I'll show you that with the coil of wire that's carrying a current, this can also produce a magnetic field, which has similar looking field lines. So for that, I'd like to then turn to this demonstration. So what we have here is, again, a coil of wire. And then we have some, I guess, these are small magnets. They're welding rod? Okay, so small pieces of steel. And what we can do is we can turn on this power supply so that we will be able to run a current through this coil. And then there's a switch in the back. I've been told it sometimes sparks. So don't be surprised when that happens. Let's see. Okay, we turn it on, and you can see those. This is a really beautiful demonstration. I like this a lot. But you can see that those small pieces align with the magnetic field. And then we can disconnect it. There is the spark. And then some of them stay because there's nothing causing them to change their direction. We can wave the permanent magnet around to randomize them again. And then you can try it again. There you go. And that's a nice way of visualizing the magnetic field that's produced by this current. Okay. Thanks. So this is a way of showing that you can use current to rewrite your magnetic memory to switch between storing ones and storing zeros depending on the direction that you apply the current. So that is a good question that we ask our freshman physics class. How do we determine the direction of the magnetic field? So we use the right-hand rule. So you take take your right hand. So that's the important thing, because if you use your left, you'll get the opposite and wrong answer. So you have to remember, use your right hand, and you're going to put the fingers in the direction of the electric current, and then your thumb will point along the direction of the magnetic field. So this works for this coil of wire. It also works if you just had a straight wire. But the general thing to remember is that if you have moving charge or current, which is made up of moving charges, that this can produce a magnetic field. Okay, so I think this helps support why magnets are good for storing information. So if I wanted to remember something like a password or a name, I'm bad with remembering names, but if I want to remember something, I don't want to forget it too easily. But the information that I'm remembering, I might want to change or update it. So if it's a password, definitely want to change or update it from time to time. But then also be able to access or read it when I need it. So if I store something, it's not useful to me if I can never remember it or read it again. So it needs to be something that I can actually access and get that information when I need it. So, so this brings me to the part of the talk where I explain how magnets work. So what is in a magnet? What is actually in this permanent magnet that causes it to behave the way it does, where it remembers its direction, even in the absence away from any power sources and even away from any applied magnetic fields. So what is in the magnet are atoms and electrons, and those atoms behave like small bar magnets as well. So you can think of the atoms as being like these small pieces of steel rod, and so they each have a spin and a direction. And where that spin comes from is a combination of a couple things. So there is both an orbital angular momentum, so the fact that the electrons are moving around the center, the nucleus of the atom. The electrons are charged, of course, and they're moving. So like a current-carrying wire, they also produce some magnetic moment by moving in those orbits. And but in addition to that, there's another component that's a little bit mysterious, which is the intrinsic angular momentum. of the electron, or spin, which is what we call it. And the reason we call it spin is because you could think of it as not just the fact, so there's the orbital component of the electron moving around the center of the atom, but then the electron itself has some spin. And so one way to visualize that is, well, maybe the electron is spinning on its own like a top. We know that's physically not what is actually happening, but it is, I guess, a good way to think about why there might be an intrinsic angular momentum of the electron on its own, outside of its motion. And spin, of course, was really a phenomena that you need that helped in developing quantum mechanics to understand. And it's quantum mechanical also in the sense that if you were to measure the spin of an electron, you would, of a single electron, you would either get two values. So if you were trying to measure whether the spin was pointing up or down, you would either measure an up or a down and no value in between. So it's also quantum mechanical in its nature. So if we have a crystal or a material that has atoms with spin, you can think of that material as looking something like this, these steel rods. And those spins could orient, they can have a direction, and that direction could be influenced by an external magnetic field. So either this permanent magnet or this solenoid can cause those spins to either align with the magnetic field or against the magnetic field. So we have special words for with or against, paramagnetism and diamagnetism. But then the one that's a little bit more interesting for magnetic storage is ferromagnetism, which is where the spins actually, even without an external magnetic field, they cause each other to align. So they keep that direction, even without any applied magnetic field. So what I'm showing now is what we call a hysteresis loop, so how magnets remember. So what happens is that you can see in this diagram that there are these small arrows on these curves. So I think my laser pointer is not working, but in any case, you can start in the middle of this box with a material that's not magnetic, or where the spins are just pointing in random directions. And then if you apply an external magnetic field, which would be your horizontal axis, you can then cause those spins to start aligning with that magnetic field. And if it's a ferromagnetic material, when you apply a large enough magnetic field, eventually all the spins will become aligned. And you can't increase your magnetization anymore because they're completely aligned. The magnetization can't get any bigger. It's 100%. And then the interesting thing with a ferromagnet is then if you start turning off the applied magnetic field, so if you start moving from right back to left, so that would be this top curve, and then the one that continues to the left, they actually stay oriented even when the external magnetic field is 0, and they stay oriented even when that magnetic field is small but in the opposite direction, until you apply a large enough magnetic field in the opposite direction that you cause the material to switch from the North Pole being on one side to the North Pole being on the other side. And so the way to visualize this is that those spins are either all pointing in a ferromagnetic material in one direction until you apply a large enough external magnetic field that you can cause them to switch to pointing in the opposite direction. So, okay. So this is how magnets remember, and the reason that they remember is because they want to stay aligned, and the reason they want to stay aligned is because it would cost energy for one of those spins to decide, okay, I'm not going to point in the same direction as my neighbors, I'm going to just flip. Nope, that's not allowed. You don't have that's not energetically favorable. However, there is a way to make magnets forget, which is to put energy into the system. So if we take a ferromagnetic material and we heat it enough so that there's more energy and those spins can become randomized, and the material can also lose its magnetism. So to demonstrate that, I have a cylinder of gas and a flame. So this is a pendulum, and as you can see, it's magnetic, so it's being held in place by a magnet that's keeping it from falling. So the safety glasses are here, that's handy. And so I'm going to show what happens when we heat up this magnet. And so I need ingredients, I need flame, and I need to be able to turn on this gas. Okay. All right. There we go. So when it's in the flame, it's heating up until it loses its magnetism, and then when it loses its magnetism, it falls away. But then, because it's connected as a pendulum, it'll swing back. And I guess during that swing, it's cooled down enough that it can become magnetic again and then stick until it sits in the flame long enough to heat up again. Okay. Great, thanks. Having the magnet in a strong magnetic field is one way to magnetize it. So here we have this handheld magnetizing device. And if I put this steel rod through it several times, I should be able to pick up a few paper clips. I've been able to magnetize it. And then, interestingly, it also has a slot called demagnetize, which probably has some randomly oriented domains, so that when I put it through a few times, I can demagnetize the rod. And there we go. Now it can not pick up any paper clips. So you can do a similar demonstration. So these are kind of nice. It's kind of hard to see unless you're up close. But this is a glass tube, and inside are some iron filings. So it's kind of analogous to what I was talking about how a material has a bunch of aligned spins that can be aligned. But here we actually just have a powder of iron, and if I shake it up, then of course they won't have any preferred direction. Okay. And they won't have much effect on this compass needle. But what I can do is then I can take a permanent magnet, and this is fun to play with, so you may want to check it out after the lecture and see it yourself. When you bring up the permanent magnet, you can see that it actually both attracts these iron filings and also causes them to align. And then it should become more strongly magnetic when all the iron filings are aligned and thus, pointing in the same direction and working together. Okay. Okay. So the next thing you need for having a good memory is being able to read the magnetization, to read the information that you've stored. And one way to read a magnet is in a hard disk drive. You can see that there's an arm. So the hard disk drive is a platter, a disk that can spin, and in the disk is a bunch of small magnetic sections that can be magnetized either one way or the opposite way to represent the ones and zeros. And so the density of information that you could store on these hard disks has increased a lot. So from 2,000 bits in 1956 per square inch in 1956 to 1.3 terabits per square inch in 2015. And so being able to increase that density makes it possible to store your, as many videos or photographs as you like. So that's very handy. But what makes that possible? So it's a couple of things. First is being able to make those magnetic bits smaller. So finding good materials that can stay magnetic and store that information even when it's shrunk down in size. And the other component, though, is also being able to read that information because when you've made something smaller, you've also made what you can sense smaller as well. So just the same way that, if in a book you have your particular size of print that you can read, if you make that print too small, you wouldn't be able to read it. So the same way with these magnetic domains, if they were made too small, you wouldn't be able to read them either. And so the first hard disk drives actually used sensing of mechanical force of the magnet with the magnetic bit. So there would be a magnet on the hard disk drive reader that would sense the mechanical force exerted by the magnetization, whether it was the North Pole up or the North Pole down, or North Pole left or North Pole right. So this, I guess, is another technological advance, was being able to either have the magnetization pointing in the plane of the disk or out of plane of the disk. The other very important advance that was discovered is spin valve giant magnetar resistance, or GMR. And this is the technology that's currently used in all read heads these days. And what was discovered was the following. So if you made a sandwich of two magnetic materials separated by a non-magnetic normal metal, there are two possibilities. You could either have the magnetizations of those magnetic layers be parallel with each other or anti-parallel. And what was discovered is an interesting effect, is that if you then sent a current through the sandwich on the left, you would see that versus sending a current through the sandwich on the right, where they're parallel, you would see a difference in the resistance that you would measure. And the way to understand that is that you can imagine that from the situation on the left, you have some spin polarized electrons that are coming from the fact that the magnet is magnetized up, and those spin polarized electrons, when they come to the magnet that is magnetized down, they feel like a filtering effect. So they get scattered and they don't go through. And so that is why you get high resistance as compared to the other situation where the two layers are parallel. You can have a low resistance. And so now you can directly electrically measure the direction of a magnet instead of having to rely on being able to measure its mechanical force. And so this is a more sensitive way to measure magnetization. And so this is also allowed for making hard disk more dense and being able to store more information. And so this discovery was recognized with the 2007 Nobel Prize to Furt and Grunberg for their discovery of giant magnetar resistance. So to summarize, so why are magnets good for storing information? Well, they are able to accomplish all of these components. They don't forget too easily unless you heat them up really hot. So putting your hard disk drive in a fire is not a good idea, but short of doing that, it should retain its information for a very long time. You can also change or update it, so either by using a strong enough magnetic field or by using a current as an electromagnet, you can change the direction of the magnetization. And then finally, we're also able to access and read it, either from the mechanical force exerted by the magnet or with this giant magnetoresistive effect. So then the question is, well, what's next for magnetic technologies? So we have this spin valve giant magnetoresistive effect. And an interesting thing about this picture is that I mentioned what happened to the current, whether it's low resistance or high resistance, depending on this alignment. But it turns out that spin polarized current can also affect the magnet. So just like when you throw a tennis ball on the wall and the tennis ball bounces back, the wall actually moves a tiny, tiny, tiny bit as well. And if you threw enough tennis balls at a wall, you could actually move the wall. That would take a lot of tennis balls. But you can imagine that the same thing happens with a spin polarized current. So if you have a small spin polarized current, it doesn't completely switch the magnetization, but it will kind of push it a little bit. And that is called a spin torque. And you can actually use those pushes to create microwave oscillations. And however, you can also exert a large enough torque to actually affect and switch the magnetization. And researchers are very interested in that because it turns out that can be more energy efficient of a way to rewrite a magnetic bit than just using the field that's produced by a current carrying wire. So this would be spin transfer torque. And then there are also proposals for making logic devices based on this as well. So you can have your input elements be magnetic bits. And then depending on whether those inputs were aligned or anti-aligned, you could have, so they could be, they could then have different effects on magnetization further down the line, which is the proposal for all-spin logic. There are other directions as well. So in my research group, we are studying semiconductor channels and how spin polarized currents behave in those channels, and using electric fields to control and generate spin polarization in those channels. So with the giant magnetoresistive effect, the layer in between the two magnets was a metal, but if you make that layer a semiconductor, you have a lot more control over the electrons inside the channel as well. And then there are also other ideas for, instead of just having the material be completely aligned one way or the other, there can be more complicated arrangements of the spins. So there are also proposals for magnetic racetrack memory. And then another proposal is that's being investigated are the idea of using what are called skyrmions. And you can see that there are, in these diagrams, a couple of different types of skyrmions. So what they have in common is that the center spin, thanks, Monica, is in blue, and it's pointing down in both of these. But the spins in the intermediate region, like how you get from the middle to the outside, is different. And the reason that this could be a robust system is that it's topologically protected. You can't smoothly deform this arrangement and get rid of it. However, researchers are figuring out ways of both creating these skyrmions and moving them around so that you could do logic operations or storage operations with these spin textures as well. Okay, so I think with that, I'll kind of summarize what I've talked about. In this talk on spins, magnetism, and computers, So we currently use magnets for information storage, and the way the magnets work are due to aligning spins or magnetic moments inside materials. And there are future spin-based technologies that are exciting and are currently being investigated. And with that, I'd like to thank you for your attention.